So we're going to talk about a classic problem in computer science. It is searching a maze. So let's say you've got this maze and it has, it's broken up into these squares. Right? So you have a start square A and your goal I. And the point of the maze isn't just to find the goal, it's to find the path to the goal. So what we want to end up doing is actually find this path A, B, H, I. And so this is a classic recursion problem, and we use something that we call, you might have heard it called depth first search, but you have to solve this problem recursively. You can't just iterate through all of them and find the path you want. You have to go make recursive calls to search through this. So I got when this was a problem for us, I got a lot of questions asking, how will this guy possibly know about this guy, right? Because each, let's say we've got a class for squares, right? And the interesting thing about this problem is that each square only knows about its neighbor. So this, it's got a list of squares, and then we'll call that neighbors, right? And so A only knows about B, B only knows about C and H, D only knows about E and C, and so on and so forth. So the question is, how does A get to know about H, and how does it end up getting to know about I? How do we get from this guy to a path that leads us to this guy here, I? And so the simple answer is we do it recursively. So A knows about B, and B knows about C and H, and then H ends up knowing about I. So to kind of show you how this searching goes, one of the things we need to do is define a base case, right? So what A will have, it'll say that if A is on the path, then add it to our list of our list of squares, and if none of its neighbors are on it, then don't add to the list of squares. So I'll run through an example, and hopefully that'll be a little bit more clear. So let's start. Let's say we have a big list of squares. So let's say we're starting off with A, right? And A has a neighbor called B, right? So A will call search on B, so it'll see if B contains the path, and so B will now search its neighbors C and H. But before it searches H, it has to search C, just because that's the order of the of the neighbors here. So B will do a search on C, right? But then C has to do a search of its neighbors. So C will do a search on its neighbor called D. So it's neighbor D. But then before D knows if it's on the path, then it has to search its neighbors E and G. So it has to search neighbor E. But then before E knows that it's on the path, it has to search its neighbors G and F. So it'll search G here and F here. So this is one of our base cases where G has run out, it's completely out of neighbors that aren't searching. So G is decidedly not on the path. So now E, after knowing that G is not on the path, will search F. So F will no longer be on the path. So F is out of neighbors. So F is not on the path. So since you can see that all of E's neighbors are not on, not the path to our goal, E does not end up being on our path. And so now that the search for E is over, D has searched all of its neighbors, and D has decided that D is not on the path. And we can kind of go, you might be able to see where this is going, but C knows about D, so C has searched all of its neighbors, which just include D, and that's not on the path. So C is done searching. Okay, so B has finished searching this entire, it finished knowing about all its neighbors. So all these guys are decidedly not on the path. But B still has one more neighbor to search. So even though it searched C and all of its neighbors turned up negatively, then we still have to search for, in H, which I'm hopeful for H. So we'll look in H. And so H will search its neighbor I. And wonderfully enough, I, which is our goal, is definitely on the path because since we're searching for the end goal, the goal square is clearly in the path. So I is on the path. Right. And now that H knows that one of its neighbors is on the path, H is most certainly on the path now. Right, so in here, we would maintain a list. So, I would be on the list, H would be on the list, and then, B, even though its neighbor C is not on the list, H is on the list. So as long as one of its neighbors is on the list, it is on the list of our solution. So B is on the list. So add B here, and then just got enough chalk space, but and then B is on the list. And so A's neighbor B is on the list, so we know that A is on the list, obviously. So you can kind of see here that A isn't going directly towards I, but it's searching all its neighbors, and the neighbor is searching all of its neighbors. So you have to make a recursive call to a function called search. That search would take in a square, and then the square has all its neighbors. And so we'll show you the code for that in our next session, but hopefully this gives you a better idea of how this kind of recursive problem ends up working out. So, thanks.